Okay, so this is York College, Chem 108, Chemical Principles 1. This is April 30th, 2015, and we are continuing in Chapter 8. So, last time when we started Chapter 8, we talked about different periodic trends like atomic radius and ionic radius, and effective nuclear charge and shielding, right? So then the last one we looked at was ionization energy. So ionization energy is the amount of energy needed to remove an electron. The higher the ionization, bigger, higher, larger ionization energies means it takes more energy to remove an electron. That means the electrons are more tightly held. So ionization energy is a general term that refers to, any electron. We can talk about specific ionization energies. So the first ionization energy refers to the energy it takes to take away one electron from the atom. Right? And the second refers to removing, once the first one is gone, how much energy it takes to remove the second one. It's not here, but the third is going to be once the first two are removed, how much energy it takes to remove the third. And so now we have a lot of different considerations. Right? In the previous trends, we were looking basically across the table and up and down the table, and we'll still be doing that here. But we're also going to be thinking about the first ionization energy versus the second versus the third, and so on. And so the principle here is the most important principle is the octet rule. Right? And so the octet rule says that if you have 8 S&P electrons, or in other words, a noble gas configuration, that you're energetically stable, you're happy. So these guys in or I don't know if they're male or female, but these elements in the first column, first family, the alkali metals, group 1, it's very easy for them to lose one electron. Right? And so in general, those group 1 elements are going to have the lowest first ionization energy. That correlates to what we know about what kind of ion they like to form. Right? Those group 1 elements like to form ions of charge +1. That's because when you lose one electron, you get a charge of +1. Now, what about the second ionization energy for a group 1 element, say sodium? Right? Is the second ionization energy going to be small or large? The second ionization energy is the energy that's necessary to remove the second electron after the first electron's already been taken away. Right? So sodium has a very low first ionization energy, right? Because it likes to lose one electron. What about the second ionization energy? It's going to be really high. Why is that?
Because you have 2 electrons into it, so it's going to be a little harder to pull away one electron.
That's true, right? That's what this says. For a given element, the first ionization energy is always less than the second, is always less than the third. But for sodium, it's going to be particularly hard. Yeah.
Because it's easy for the first one because it wants to lose it, and then the second one is tightly housed, so it's going to be harder. It doesn't want to lose that electron because it wouldn't be stable anymore.
This is true. So, yeah.
Is it because of the second shell? Because one S holds up to 2 electrons, and then for Mg, it goes up to
We're not talking about Mg. Right. Mg that's the next thing. But that's right. But why does it like to lose the first one but not the second one? That's correct.
After it loses the first one, it's going to have all its last outer shells filled?
Mm-hmm. So once it loses the one electron, it has the same electron configuration as – 'neon, the noble gas. Once it's in that configuration, it has the same electron configuration as neon, the noble gas. Once it's in that configuration, it has the same electron configuration as neon, the noble gas. Once it's in that configuration, it has the same electron configuration as neon, the noble gas. Once it's in that configuration, it has the same electron configuration as neon, the noble gas. Once it's in that it's stable, right? Because it has a complete octet. It has a noble gas configuration. It really, really doesn't want to lose that. So that's why it doesn't want to lose the second one. So those group 1 elements are going to have a low first ionization energy, a high second ionization energy. What about magnesium? Right, magnesium, compare the first ionization energy of magnesium to the first ionization energy of sodium. Which one's going to be higher? Magnesium's going to be higher. Because if you take 1 electron from magnesium, it doesn't have a complete octet. What about, whereas if you remove 1 electron from sodium, it does. What about the second ionization energy? Magnesium is going to be lower. And what happens when you take 2 electrons away from magnesium? It becomes stable. It takes the neon configuration. So, okay, so here's the basic, sort of the first level of understanding. Okay, so let's think about trends. Ionization energy decreases down a family. So as you go from lithium to sodium to potassium to rubidium and so on, as you go down the column, down the family, the first ionization energy decreases. That means for cesium, which is down at the bottom of the table, it's easier to remove the first electron than it is for lithium. And the reasons for that, we can think about it 2 different ways. One is as you go down the column, n increases. Right? As n increases, your distance from the nucleus increases. Right? And so you're already further from the nucleus. It's going to be easier to grab you away. But also we have another argument that has to do with shielding, or Z effective. Right? As you get further from the nucleus, what happens, you get more and more layers of core electrons. And as you get those more and more layers of core electrons, you get more shielding of the nuclear charge, so the valence electrons are going to be not as tightly held. So as you go down a family, electrons are held less tightly. As you go across a row, across a period, the ionization energy increases. And one way to think about that is as you go from left to right, you go from metal to nonmetal. Right? And metals like to lose electrons. Nonmetals don't like to lose electrons. They like to gain electrons. But there are some exceptions. 2 of them that we'll consider. First is there's special stability of closed subshells. For example, if you're boron, you're 2s to 2p1. That's not very happy. It doesn't mind, boron doesn't really mind losing 1 electron, because when it loses 1 electron, it becomes just s2. Right? And so it has a closed subshell, closed highest subshell. So s2p1 electrons, such as boron, are easier to remove than s2 electrons, like beryllium. Right? So beryllium has in its atomic state, right, 2 electrons, 2 valence electrons. Those are both s electrons. Once you remove 1, you break that closed subshell. Not too happy. The second special stability is the stability of a half-filled subshell. So for example, if you have p4, remember how many p orbitals do you have? You have in each level, you have 6 p electrons. You have 3 p orbitals. Right, so 6 possible electrons. If it's half filled, it's going to be p3. And when it's p3, you're going to fill them 1, 2, 3. Right, you're going to have this parallel spin special stability. So you have the half-filled subshells. There's a special point of stability. So p4 electrons are easier to remove than p3 electrons. When you remove a p4 electron, you get to a half-filled shell. When you remove a p3 electron, you move from a half-filled shell to not a half-filled shell. So, whoa, that's no good. Well, can you see that at all? No. Okay. Okay. So, let's go across a row. Right, so we get helium, lithium, beryllium, boron, carbon. I'm going to run out of space, so let's do it the other way. No, that's not from helium. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Right, so we're going from basically group 1 to group 8. The first ionization energy for lithium, we don't have to memorize these, right? We're just looking at the trends, is 520. And these are, I think, in kilojoules per mole. 520. Then beryllium, 899. Boron, even though it's the effective nuclear charge would say that it should be easier to remove. I mean, it should be harder to remove. It's actually slightly easier, 801. Right? This is because you're going from 2s2, and this is 2s2, 2p1. So removing the 2p1 electron is okay, not too bad, because you're landing at 2s, a closed subshell. Carbon, 1086, nitrogen, 1400. Oxygen, 1314. And so this is the second special point of stability. The nitrogen is 2s2, 2p3. And the oxygen is 2s2, 2p4. And so the P3, here you have a half-filled subshell. Here you have a half-filled subshell plus 1. Right? So when you remove one electron from here, you get a half-filled subshell. It's happy. Reasonably happy. If you remove one from here, and that becomes 3, right? We remove from here, it was 3, now it's 2. It was kind of happy, now it's not happy anymore at all. And so it goes down. And then fluorine goes up, 1680, neon, 2080. Right? It's not very happy at all. Okay, what about the second ionization energy? Well, the second ionization energy for lithium, look at that, 7,300, enormous. That's what we just talked about, 2 or 3 slides ago. The second ionization energy for group 1 elements is going to be really, really high. But then after that, what do you have? You have 1757, and then 2430, and then 2350. So it's increasing, and then what happened here? It decreased. Why did it decrease here? Carbon is 2s2, 2p. 2p what? 2p2. What happens when you take away 2 electrons? It's happy. You get to 2s2. You get to a closed subshell. So the dip that occurred here between BE and B for the first ionization energy, because you landed at 2s2, occurs here for the second, because you take 2 away from carbon, you land at 2s2. Let's get 2350, 2860, 3390, 3370, because when you take 2 away from fluorine, you land at a half-filled subshell. And then For neon, it's going to be large, 3950. And so that's explains that explains the trends plus the exceptions to the trends. Okay. The next, and I believe this is the last trend that we're going to look at, is called electron affinity. Electron affinity measures the tendency of an atom to gain an electron. Right, so this is the opposite of ionization energy. Ionization energy is how easy is it for an atom to lose an electron. Electron affinity is how easy is it for it to gain an electron. So as you go down a column, the electron affinity usually decreases. Right, and that's because, but that's not always the case. Mainly because you're getting further and further away from the nucleus, it's easier to kind of like sneak an electron in there. Across a period, the electron affinity is going to increase. Right? So it's going to be easier as you're getting, okay. So electron affinity, let me say this again. Electron affinity generally decreases down a family. It's the opposite of ionization energy, essentially. So you have more shielding and so on. And so it's easier to lose an electron, it's harder to gain an electron. You have less effective nuclear charge. Across a period, the electron affinity increases. And this kind of makes sense, right? Because nonmetals like to gain electrons. Metals don't like to gain electrons. So again, it's going to be kind of like the ionization efficiency. It's going to, except the trend is backwards, right? It's going to increase as you go from left to right, but you're going to have special stability of the closed subshell, and you're going to have special stability of the half-filled subshell. And noble gases essentially have an electron affinity of 0. Why is that? They're already happy, right? They don't want to gain another one. They already have their octet fulfilled. So, for example, the electron affinity of beryllium is less than that of lithium, right? Because beryllium is 2s2, right? It has a closed subshell. Lithium is 2s1. If it gains one more electron, it's going to have a closed subshell. So lithium likes to gain its electron to get to the closed subshell. Same thing for the half-filled, yeah.
If lithium gained an extra electron, would it have the same would it still have the same energy level as magnesium, or would it be a little different?
It would be different, right? I mean, the overall energy would have to be different, right? Because the charge, if you consider the proton, right? The protons, you're always going to want to avoid it. When you draw it in the chart, it's going to be the same, right? But if you have 10 electrons and 9 protons, that's just not going to be as happy as if you have 9 and 9 or 10 and 10. Right? Okay, so here's the trends in electron affinity. So you can see lithium is 60, beryllium is about 0. And then it increases, 27, 122, 141, 328. And nitrogen also is an exception, because nitrogen is already at a half-filled subshell. It doesn't want to gain another one. So from here to here, it increases, right, with the exception of the half-filled subshell. And this one it's not too bad, because once it gains one electron, it gets to the it gets to the closed subshell. And the trends go basically the same as you go for this column, this row, this row, this row, or this row. Okay, so that's the end of the slides. Let's do a couple of examples, or a couple of problems. Yeah?
Just got a question, like fluorine, I know it has the most electronegativity, like one, but why is chlorine more than fluorine?
That's a good question, and I'm not entirely sure of the answer. Electronegativity and electron affinity are not quite the same thing, right? Electron affinity is the ability to gain an electron. Electronegativity, which we're going to see in the next chapter, is how much it likes electrons when it's in a covalent bond, right? Not isolated. The reasons are not straightforward, I think, and so that's why we put in this line over here that says electron affinity generally decreases down a family, but not always. And so what does that mean? That means when it comes to an exam, we're not going to ask you about electron affinity in a column, right? Because that's a little bit unusual, right? Chlorine has the potential to have d orbitals, right? D orbitals where fluorine doesn't, right? And so there's other things involved there. Okay, so put these in order of increasing atomic size, Li, C, and F. Which one is the smallest? Lithium or fluorine? Fluorine is the smallest. So it's going to be fluorine, then carbon, and then lithium. Remember, as you go from left to right, what happens to the shielding? The shielding decreases. The effective nuclear charge, therefore, increases. If the effective nuclear charge increases, it's pulling the electrons tighter, so the size is going to decrease. Okay, so increasing ionic radius, let's look at Li plus, Be2 plus, and F minus. Remember, in ionic radius, you're looking at two things. You're looking, you're looking mainly at the charge, right? But it's not a straight trend like this because you're starting with cations and then you're going to anions. It's sort of no. No. What's going to be big? What's going to be really, really big? Fluorine is going to be big because anions get bigger, right? Cations get smaller, anions get bigger. So the biggest one is going to be your F minus. What's going to be the smallest one? So it's going to be Be2 plus Li plus. You notice that we're comparing, they're all in the same row, right? They're all in the row 2. Once you start going from one row to the next, it becomes quite hard to predict sometimes. It's going by the charge. Remember, the greater when you have more protons than electrons, what happens to the size of the element? It gets smaller, right? Because the protons are pulling on the electrons. If you have more protons than electrons, the whole thing gets smaller.
So ionic radius is basically the same as saying size of the
Size of the ion, yeah.
Oh.
Yeah, not size of the atom, right? Size of the ion. Okay, so let's say increasing first ionization energy, let's say K, Ca, Se, Br. Br. Mm-hmm. Mm-hmm. Yeah. So that's basically, remember, ionization energy, the higher the ionization energy, the harder it is to remove an electron. Right? So the easiest electrons to remove are generally going to be the metals. Right? So K is the easiest, and followed by Ca is a metal. And it doesn't really like to lose one, but it can lose one. And then Se, yes?
So the first ionization energy is how much energy it takes to lose the first one?
Yeah.
You're saying K is the highest energy to lose one?
No, backwards, right. Yeah. K is the lowest. K, Ca, Se, Br. Right, so, yeah, the lowest energy to lose one. Right, and then Ca, and then Se, and then Br. You notice that here we didn't encounter any of those exceptions. Right, what if instead of K, Ca, Se, and Br, we were to say K, Ca, and Ga? What would you expect? That's Ca and Ga. Yeah, you would expect K and then Ga and then Ca, because you have the closed subshell thing going on here, right? Ca is going to be 1, 2, 3, 4, right? It's going to be 4s2, and Ga is going to be 4s2, and then some Ds, right? And then, but let's just say 4s2, 4p1. So it likes to lose the p1 so it can get to the closed subshell, right? Whereas 4s2, it's already at a closed subshell. You take one away, you break the closed subshell. So there you have the little funky break in the trend. Let's say increasing second ionization energy. And let's look at sodium, magnesium, and aluminum. So that's this. Remember, this is the second ionization, so the energy to take away 2 electrons, or the second electron. Mg is going to be the lowest, right? Mg likes to lose 2 electrons because it's in group 2. So the lowest is definitely going to be Mg. What's next? Al. Then Na. And we know Na is really, really bad because once it loses 1, it's happy. It's got its octet. And so it really doesn't want to lose a second. And then Al is kind of intermediate, right? Losing 1 puts it okay. It's closed subshell, but still, that's closed subshell is not as good as a closed shell. Yeah.
So would Al still be better than Ca if it's K, Ca, Al?
That's hard to predict because they're not in the same row.
What about gallium?
So Al would be, as you go down the column, it gets easier to remove an electron. Yeah, so because there is greater distance and more shielding. So Ga we would expect to be lower than Al.
Lower energy to take.
Lower energy to take one away.
No, what about, I'm talking about, so let's say it's potassium, calcium, and then gallium.
Yeah. Same thing. You would expect calcium to have the lowest second, then gallium, then potassium. Right. The first row is always going to have a really horrible second ionization energy. All right. So you guys know all about Chapter 8 now. Which means what's that? Yeah, you can, because we're going to take a break now.